So we consider the electron contribution to the specific heat in solids. It's not easy to give a general answer to that because solids can be very different with regards to their electronic behavior. In particular, we distinguish insulators and metals. There are also, of course, semiconductors, but let's keep to these types now for the time. And the insulators are the ones in which we have occupied bands, so they are always occupied by the electrons. And there are also conduction bands which are always empty. They are not really conduction bands because there will never be an electron in those. And because of this rigid solid structure, the temperature will not change the occupation of the levels in an insulator. And so we don't have a significant contribution of the electrons to the specific heat. But in the case of metals, that's completely different because there is a continuous density of states across the Fermi level. And in this movie, I would like to analyze that situation in metals, where we use the free electron model for the electrons. Here you see the Fermi Dirac distribution. It's FFD, and then we have sketched it here with on the horizontal axis E divided by the Fermi energy. Note that the Fermi energy is a kind of chemical potential. It's the chemical potential at temperature T is 0. So EF is the mu at T is 0. In metals, usually the temperature is much smaller than the Fermi energy. KBT is much smaller than EF, which means that the distance over which the Fermi function drops to 0 is much smaller than the Fermi energy itself. And that is called a degenerate Fermi gas, because most of the states here are maximally occupied. Obviously, if you would know the dispersion relation of the electrons as it comes out of band structure calculations, for example, you could do accurate calculations for the specific heat and the total energy of the electrons. However, in order to make progress with analytic calculations, we assume that the electrons are free. So we have just a free electron gas, and that's a very good model for most simple metals, such as aluminium. Let us first analyze the extreme case where we have T is 0. That means that we have a filled Fermi sphere. The Fermi Dirac distribution is 1, which means the maximum occupation for all the k vectors that are smaller than some Fermi k vector. And the Fermi k vector can be related to a Fermi energy, epsilon f. And it's 0 outside, so 0 for energies higher than the Fermi energy. In order to find the value of this Fermi wave vector, we just count the number of particles. We know that there are n electrons in the system, and those n electrons should occupy all the states which are below kf. And then we have an extra factor of 2, and that factor of 2, not surprisingly, represents the spin degeneracy, because we have a spin up and spin down for each k vector. And now we need to sum over all the Fermi states, the wave vector states inside the Fermi sphere, and replacing again the sum by an integral as usual, we have again a integral here over a sphere with radius kf, so we have a volume of 4 over 3 pi times kf to the third. And putting everything together, it relates the number of particles to the Fermi sphere and the volume. In fact, it's a relation between the density, n over v can be related to the kf to the third. So if we want to sum over all the states available to the electrons of some summons, some ... here, we can replace that by twice the sum over all the k vectors, 2 because of the spin. And if we then replace the sum over the k vectors by an integral, we have this integral. And now we can use something else. We can use the fact that h squared, k squared over 2m, because we have free electrons, that is the energy of the electrons, and that allows us to write this integral over k as an integral over the energy, and that will be this integral then. And if we work out that form, we arrive at this expression here, and we see that there is a square root of epsilon here, and that's all these constants in front of the integral, and this, together with the square root of epsilon, we move those into to a function g of e, and that function, it's well known, that's the density of states. So it tells us how many values, how many levels, how many states there are available to the electrons with energies in this small energy interval delta E. So G epsilon times D epsilon gives us the number of states available to the electrons in the interval delta epsilon. So if we summarize the result, whenever we have a sum over all the states of the system, we can replace that by an integral over the energy involving this extra factor of g of e, and g of epsilon, that's a constant times the square root of epsilon. The boundaries of these integrals are between 0 and epsilon f, and that is because we have so far focused on the situation where the temperature is 0 and all the states up to EF are filled. So let us now have a look at the energy for temperatures above 0. Then we need to solve over all the energies, and we need to sum over all the k vectors, and all the energies are weighted by a Fermi Dirac distribution function, so 1 over e to the power beta epsilon k plus 1. And that function at t0 cuts off beyond the Fermi energy. But now it's a soft cutoff. The softness is governed by this parameter beta, which is 1 over kBt. And so we can write this again in the form of an integral, where we have replaced the sum over k by an integral over ge delta E. And instead of having a hard cutoff here, we have now a soft cutoff given by the Fermi function. For further analysis, it turns out to be extremely useful to write this in a somewhat different form. We write it now as two integrals, where the first integral we have replaced the epsilon by the epsilon f. So we have changed the result, and in order to compensate for that, in the second integral we have the old integral over epsilon, the original one, and we subtract the result that we put here. And if you carefully consider this, you see that if we would put epsilon f in front of the integral, then this integral just counts all the numbers of it sums over all the states times the occupation, and that gives us the number of electrons. So the first integral simply gives us the result n times epsilon f. And the second integral has this epsilon minus epsilon f, which also occurs here in the exponent, and so that's why this step was convenient. Now I've been cheating a little bit in the derivation so far, because I've put here an epsilon f, and that epsilon f is the chemical potential at temperature T is 0, and what I should put there is the mu, the actual chemical potential at a certain temperature. So I have assumed that the mu only very weakly depends on T. Let us assume that for the moment, and let us keep the epsilon f just as a number, and later I will go into the analysis of mu, and in particular its temperature dependence. That point is very important when you calculate the specific heat, because if you neglect the temperature dependence in this epsilon f here, then this term doesn't count for the specific heat, and we only have a temperature dependence in this beta. And so that's the only term which occurs, which has to be taken into account when we take the derivative of the energy with respect to the temperature, and that's what we need to do when we find the specific heat. Taking the derivative of E with respect to T is a little bit of work, and what you arrive at is 1 over kBt squared times this integral, which has now an epsilon minus epsilon f squared, there is an exponent here, e to the power beta epsilon minus epsilon f, and the denominator obviously has got a squared. So when I divide the numerator and the denominator by this exponent, it turns out that the expression reduces to the following form. It's epsilon minus epsilon f squared, and then here I have my denominator, g of epsilon 1 over kbt squared. And now in order to make some progress, we have to consider the form of this function here, excluding the density of state. I have encircled the integrand except for the GE, for G epsilon, that's the density of state. And that part that I have encircled is shown here in red in this plot. And as you can see, it consists of two narrow peaks which are very close to the Fermi energy. For completeness, I have also added in green the Fermi Dirac distribution, which drops from 1 to 0 at the Fermi energy, and then I have in blue rendered the G of epsilon, typical G of epsilon. Here I've used something which resembles the free electron gas in 3D. And as you can see, the density of states typically doesn't vary a lot across the region where the red part, this red curve here, is non-zero. And so we can safely replace the value of G epsilon by the G precisely at the center here, so that is at EF itself. And then we get still a good value for the integral. Here I have extracted this G at epsilon f in front of the integral, which now contains only known parts, and I can do the integral. Well, in order to simplify the expression, it's useful to introduce a variable x, which is just the exponent here, apart from the factor 1/2. It's beta epsilon minus epsilon f, or epsilon minus epsilon f divided by kt. So what happens then to the integral? So this is the result. Here we see the integral written in terms of x, and because of this transformation there is an extra factor of kbt, which together with the kbt squared here gives you now a kb squared t. So we have an x squared dx, and so we have three factors of kbt that are coming into the problem. A slight complication is the fact that the integral doesn't run from 0 to infinity or minus infinity to plus infinity, but it runs from xf is minus beta epsilon f. As you can see here, the integral when epsilon is 0, the lower bound is minus epsilon f over kbt. However, that is just the part in the original integral which would run from here to minus infinity. And so we can replace the lower bound safely by minus infinity, because the integrand is over this interval from this negative value to minus infinity negligible. The contribution to the integral is negligible. And if we replace the lower bound by minus infinity, we obtain an integral which is known, which we can calculate. I will not do that here, but the result is pi squared over 3. And the final result for the contribution of the electrons to the specific heat is written here, pi squared over 3 kb squared t g. That's the density of states taken at the Fermi energy. And what is important is the temperature dependence. We see that the electron contribution to the specific heat is linear in t. Our analysis of the specific heat for the electrons was mainly based on the fact that the only time dependence in the energy was through the beta here, and not in the Fermi energy, which in fact should be replaced by the chemical potential, and the chemical potential may assume different values when we go to higher temperatures. So now we address this point. What about the chemical potential as a function of temperature for low temperatures? In other words, we are questioning now our main assumption, namely that the mu as a function of t can be replaced by epsilon f. And we know that in order to analyze the mu, the most sensible quantity to look at is the n, that's the number of electrons that's kept constant. And so we will use that condition, the fact that the number of the electrons is always the same independent of temperature, in order to get a handle on the variation of mu. So here we see the expression for the number of particles, which is just the sum over all the energies. We multiply it by the density of states, and here is the Fermi-Dirac function. And we should note that the density of states essentially behaves as the square root of epsilon. And so this function has the following form. If it would be at zero temperature, then we would just have the square root of epsilon and then cut off sharply here at epsilon f. In this case, we have multiplied it by this Fermi-Dirac function, which smoothly cuts off around the Fermi energy. So how do we analyze this integral as a function of the temperature? And in particular, we should replace the Fermi energy here by the mu, and that's the guy we want to have. Now, in order to make progress, we define a new function delta epsilon, which is defined such that its derivative, so delta primed epsilon, is precisely the density of states. So it's an integral of the density of states. And if we have that function, we can do a partial integration and rewrite the integral of n, the integral representation of n, in the following way. So partial integration leads to the integral of this function here and the derivative of the Fermi function, which is this function that we see over here. Now we consider this function delta, which is taken here at the value epsilon, and Taylor expanded around the value mu. So we take delta mu, and this is the first Taylor expansion term, because the derivative of delta is g. So we take g at mu times the difference, epsilon minus mu, and this is the second order term, which contains the second derivative of delta, which is the first derivative of g. So here I have put the Taylor expansion in the integral in the first part. You can see this is where it derives from. And then here I have minus the derivative of the Fermi function with respect to the energy. And now we note that this function rapidly reaches 0 when I move away from mu with my epsilon. And so in particular, if I am at 0, then we know that this function is approximately 0. So if I want, I can always replace the lower bound of the integral by minus infinity. Now if I do that for the second term, I can argue that the integrand is anti-symmetric in epsilon minus mu, because this one is an odd function of epsilon minus mu, and this is an even function of epsilon minus mu. The g mu is a constant, and so I can immediately see that the second term will give me a vanishing integral. So I'm left with the first and the last term, and the first term also gives me a rather simple result. I have a delta mu, and I have a minus df d epsilon, which I integrate from 0 to infinity. F is the Fermi function, by the way, the Fermi-Dirac distribution. And I have then minus delta mu. I have the Fermi-Dirac function at infinity, where it is 0, minus the Fermi-Dirac function at 0, where it is 1. And so I simply find delta mu. So we can write the result for the number of particles as delta mu plus the remaining term of the integral, where I've used the fact that the integral of epsilon minus mu squared divided by this denominator, it's an integral that we have met before, gives me a pi squared over 3, and together with this 2 here in the denominator, I obtain g primed mu, pi squared over 6 from the integral, and then I have from the beta I have kbt squared. Now, if we have a system in which the number of particles doesn't vary if I change the temperature, then we should have that this n, which was evaluated at temperature T, is equal to the n at temperature T is 0. So the derivative of n with respect to temperature should be 0, and if I implement that in this equation, I first get the derivative of delta, which is g mu, and I have to multiply that by mu primed, where I've used the notation that mu primed is the same as d mu dt. And similar for the second one, here I have the second derivative with respect to g multiplied by mu primed, and then there was still this term here lurking around, and then I have a term where I take the derivative of this temperature dependence, so that gives me g prime mu times pi squared over 3 kb squared t. And then I note that this term for low temperatures is negligible with respect to the others because it scales with t squared, and the other terms scale with mu primed respectively t. And so what I find is the following. So we obtain the result that g mu times mu primed is minus g prime mu pi squared over 3 kbt. And the fact that g is a smooth function around the Fermi energy, so g varies with the square root of mu, so also g primed varies with the square root of mu, and at a finite value of mu, which is close to the Fermi energy, these two functions are harmless. So essentially I find that the mu primed is proportional to t, and therefore the mu will be the mu at t is 0 plus some term, some constant, times t squared. And so that means that mu only weakly deviates from its 0 temperature value, which is the Fermi energy, and it's weakly enough to not affect the validity of our previous analysis of the specific heat of the electrons in a solid.